Okay, we are now recording. Let's get it set up from the current slide. And before we Before we get going, let me make these few announcements. Okay, I think you've heard most of these before. If anyone is getting anywhere close to graduation, if you're graduating this term, this fall, I hope you've got your application in because you're really past the deadline, and I don't know if you can get it in time. Try to. You know, they sometimes can squeeze them in if they really work at it. See, things are a little different this fall term because we are having graduation exercises both fall and spring now. We used to only have them in the spring, and so the fall graduation applications were not as crucial. The time pressure wasn't there. Now it is because they've got to get everything ready for graduation. Okay, so please get those in. But if you're graduating in the spring, this is the best time to get your graduation application started anyway. What you do is do a degree audit first. You pull out your degree plan, go over it, see what you have taken, what you're taking now, and what you still have to take, and see if you can finish in one term. See your advisor about that. And here's a word. The spring schedule, we're in the process of working on it, so hopefully it will be out within a week or two. I don't know if they'll make that deadline or not, but hopefully it'll be out within a week or two. That used to be they always waited till after the second mini-term to get out the schedule. Now they're sort of pushing it a little faster. I don't know why. Okay? But once you have a senior advisor with your degree plan, gone over that, then you apply online. Okay? So please do that the term before you graduate. Whenever you're going to graduate, be sure to remember to apply the term beforehand. Now, what it enables you to do is if there's a course you're missing that you need to graduate, that way you have, make sure you can get it in your schedule. If you can't, if it's not offered, if it conflicts with another course, you can talk with advisors, instructors, department chairs, or whoever, and see if you can get it, adjusted some way so you can take that course. If you can't, then you have time to do a course substitution. And those take time. So you see, to get it started the term before you graduate, that's ideal. Okay, so please remember that as you get closer to graduation.
What was it you was just talking about there?
Who was this?
What was it you was just talking about?
Oh, it was about applying to graduate. When you're getting close to graduation, try to apply to graduate the term before you're going to graduate, not the term you're going to graduate. That enables you to get all sorts of wrinkles ironed out well in advance, and you don't get into the time pressure at the end. Now, I don't know if they're still looking for them, but they were looking for note takers for this term. So if you want to see Dr. Renee Herndon on this campus or Ms. Janine Jones on the Birmingham West campus, they pay you to take notes for students who have disabilities that prevent them from taking their own. And the Space Center is looking for peer tutors, and they pay you to do that too. So it's a great situation. You're helping somebody else. It helps you know your subject better, and you get paid in the booth. So, I mean, how can it get any better than that? So those are those major announcements there. Let me make this one here. It has to do with something I said earlier. On Friday, now the past couple of Fridays, I've been asking every Friday when I'm over on Birmingham campus, okay, when are we going to start on spring schedule? When are we starting on spring? Oh, we got plenty of time. Well, last Friday. Oh, we got to have spring schedule done next week, okay? So there's pressure for spring. Not just spring and summer schedules they want done this week, okay? Now, they also said, oh, and you got to have thus and so in for a sax stuff. Well, I tried to put it in, and it just would not go into the file. So I sent it to the dean and said, here it is, I can't get it to go in. Oh, you'll have to check with somebody on Monday and get access to it. Well, she's the one that gives access, and she hadn't given it. So anyway, I got that done. And then we got another email last week, right at the end of the week, saying, we need resumes from your instructors. And so I sent it to the instructors, and I thought to myself, I wonder if that's all instructors or just full-time. So I sent that. Oh, no, it's part-time too. Well, I have a huge number of part-time instructors. So I sent another email requesting them. They've been feeding back the information. I've been moving those over. So what's the bottom line of all this? I have my grade book was basically empty as of last Friday. Now it's that full, and I have had basically zero time to do any grading this week. And the likelihood of having any time to do grading, well, while y'all are doing your lab today, I might get a little bit done, but I haven't put anything in Blackboard lately because I've just been swamped with these other requirements. So as soon as I get my head back above water with those things, then I'll get back to this. I'm kind of hoping it rains like this all weekend, so I'll have some downtime inside that I can get some grading done, but I don't know if that's going to happen or not. This has been a strange week for me, too. There was a funeral at our church. A good friend of mine's father died. I didn't realize that he was 97 years old. So I had that funeral on Monday. My wife was out of town from Saturday through Wednesday. Something else happened. Oh, well, I guess our field trip was one thing that was unusual. But then there was something else. I don't remember what it is now.
Speaking
and then
of
all this
field trips, did you ever call Jerry Tracy regarding that?
No, I've got to see when we're going to finish the chapter. And as soon as I can see exactly what day that's going to be, which it probably will be the day, but we'll see. Then I'll give them a call and see what I can find out. May have some time tomorrow to do that. And anyway, then tomorrow we've got a wedding to go to. So it's just been a crazy week all the way around. All right, now let's just talk about what we're going to do in this class. We are going to continue on chapter 23 today. We're going to start that in just a few minutes. And then no later than 3:45, we'll stop whatever we're doing and have the lab from the last chapter. Not that it's that directly connected with it, but it's one on topographic maps. Okay? And I have a topographic map, but then there's a few other exercises you can do. So we will be doing that for the lab the last 2 hours today. Now, several of you were not here Tuesday to take your test on the last chapter, so you'll need to make those up whenever you can. If you finish the lab early today, maybe you can take them today, or if not, we're going to have a little bit of time, I think, at the end of the term, because I think we're making pretty good progress through the material. But we don't have much time left. We have today, next week, and the following week, and that's all, folks, okay? But we only got a little bit of this chapter left, a little over half of the chapter to go, and then one more chapter, plus possibly another field trip, and another lab, and 2 tests in the final. I mean, so it's going to work out, I think, pretty close. All right. Any questions on anything so far? I'm sorry?
When is the test?
The test for this chapter?
Chapter 23.
23, after we finish the chapter. I think we'll finish it today, so the odds are it's going to be Tuesday, unless we go to the Channel 13 Weather Center on Tuesday. We may still be able to get the test in. We'll see. There's a good chance it will be Tuesday, especially if we finish the chapter today. Okay. So, any questions on what we've done so far? And where we're headed? All right. There. Oh, I lost my pen, it looks like. I know I had it because there it is. Marking the roll book. Okay. So, just a little bit of reversal. Remember, I think it was last time or time before, we were actually talking about the weather makers, and one of those were the air masses and the fronts. And yesterday on the weather, on the radio when I was going home, I heard them say, because of the cold front coming through, we're having all this rain. So that's exactly what I was suspecting. We had a warm air mass sitting over us, very humid warm air mass sitting over us from the Gulf of Mexico, maritime tropical maritime, however they say it, and we had a cold front coming down from, and more than likely a continental, polar continental, however you say it, coming in from the north, and that cold air lifted the warm moist air, made instability, and that's where we had the rain. And keep having the rain. So I don't know if this is still a cold front coming in or if it's become a stationary front and they're sort of battling it out and trying to figure out who's going to win, and it just keeps dumping rain on us all the time, which is not bad because we had gotten sort of dry, especially North Alabama had gotten sort of dry. All right, enough of that. Let's go on to where we are to start today. Major storms, okay? These storms are rapid, often violent weather changes. These are the things we worry about, okay? They often are associated with a frontal passage. And my wife said yesterday she had gotten home from Vermont. We were a little concerned because Delta had had a crash of the computer system the night before she was to leave early the next morning, so she wasn't even sure the plane that she was going to take out the next day had even gotten there that night. But she did make it home. And she got home and was there, and she said a lightning seemed to strike in the backyard. It didn't hit anything, but she said it was bright flash and immediate thunder somewhere very, very close in the neighborhood. And she said it was loud. Now, I didn't hear any thunder like that yesterday. Where I was on the Birmingham campus probably at that time. I didn't hear any thunder, but I did know it was raining off and on. So rapid, often violent weather changes, often associated with a frontal passage like we talked about this frontal passage today. Three major types of storms, and these are from increasing order of severity. Thunderstorms. That's what we had when she had that lightning strike, okay? Tornadoes often are associated with thunderstorms, and finally hurricanes, okay? Now, some might argue that tornadoes are more dangerous than hurricanes, but they are in the immediate area, but not in as broad of areas. So that's the reason hurricanes are put as number one. So let's talk about thunderstorms. Usually develop in warm, very moist, and unstable air. Just describe that to you. The warm, tropical maritime air mass that we had sitting over us for so long. I mean, it was hot, humid, sticky, but we never seemed to get any rain out of it. It was sitting over us, and here came the cold front. And when the cold front came in, it sort of bulldozed and made the warm air move over the top, making it unstable, and there came the rain. And we've been having rain now for at least 2 and maybe 3 days. Okay? I think maybe at least 3 days. Okay? Possibly even more. Now, 3 stages to these thunderstorms. The first stage they call the cumulus stage, and if we had done the previous chapter, you'd recognize cumulus from the name of a cloud, a class of clouds. Now, I pointed those out earlier on one of the slides. These are associated with convection. Anyone tell me what convection is? This was something covered in the first half of the book, but y'all haven't had that. I don't think any of you have had that course yet. So, what is convection? We have mentioned it before. Second? Heat? Yes, it has to do with heat. What happens is, anytime a material, especially a fluid, liquid or gas, heats up, the molecules get further apart because they're more energetic, and as they get further apart, the density decreases. Density decreases, they rise. So basically, it can be summarized with hot air rises. Okay, hot water rises. Anything as it heats up typically rises. Okay, so that's what convection is: the upward movement of warmer air and the downward movement of cooler air. That's convection. Now, that's one thing that can cause cumulus clouds. Another thing are the other things we talked about before, the mountain barriers. The warm moist air coming in, hitting cooler surface temperatures as it goes up a mountainside, and that can create these tall, big cumulus clouds. Or the third is the cold front, what we have out there coming in. Okay, so all of those will produce, in fact, sometimes a combination of them will produce these cumulus clouds. That's the beginning stage. That's where the stage is set for the thunderstorm to happen. Now, let's get a graphic here, and that's basically this part. That's the convection. You can see the warm air moving up, and you don't see cooler air coming down yet, but the warm air is moving up, forming these clouds. It's not quite a cumulus cloud yet. That's when we call it a cumulus cloud, or maybe the other two are beginning to be. Okay? But that's what happens. Either convection, which is shown here, or it could be as it's moving up a mountainside, that's creating the effect, or a cold front coming in, and that's creating it. Okay? And by the way, the convection could be caused by these two as well. At the mature stage, the updraft that you have can no longer support what happened now. So get this now. Look at this altitude here. This is getting close to 9 kilometers in height. That's a long way up there. That's 5.5 miles up. Those are some tall clouds, and they haven't even reached the peak yet. Okay? So in that stage, as this warm, moist air is coming in, plenty of moisture in it, as it climbs to those altitudes, they chill out. Okay, speaking of chilling out, here, okay, is Justin. Okay. Now, I think I forgot to mark Dante when he came in, and he's left already, but he did show up. I think I forgot to. Okay. Forgot to mark Darren too, but he did show up. The blue line here. All right. Still haven't seen Ishmael or Zachary. Okay. Or DeAndre. All right. So at the mature stage, okay, this warm, moist air is moving up through high elevations, and guess what? It gets quite cold up there. Really, really cold. So this warm, moist air starts forming cloud droplets. That's what makes the cumulus clouds. You see them, and they go so high, they're beginning to condense. But as they move up, they also are beginning to freeze. Those little air droplets actually become little ice droplets, you might say, as they go up. So the updraft is pulling them up. That convection is taking them up. Suddenly, it's not strong enough to support the growing ice crystals. They're getting bigger and bigger, or snowflakes, okay? Now, so what happens in the mature stage, some of them start falling down, okay? Now, they may or may not make it all the way to the bottom, but many of them do, but most of them melt before they reach the bottom. Especially if it's in temperatures like this. Yeah, way up high it's icy, but down here it's nowhere close to icy. So those water droplets that were falling out there probably were one-time ice crystals, just probably minutes before they fell. Okay, so that's what's happening. So now the falling frozen water melts, becomes rain. Now, here's something that when this is happening is pretty dangerous. Okay? When you have the updraft and then they start to fall and then they get more updraft and then they fall and more updraft, what happens? Every time that happens, they get bigger and bigger And that's what forms hailstones. And they get taller and taller. And finally, none of that updraft can support the hail anymore, so it comes crashing down. It doesn't have a chance to melt, and it actually falls as hail. When that's happening, you know you got a monster storm out there. You got a monster cumulus cloud that has produced that kind of. So hail, yeah, hail itself is bad enough, but it's indicating that's a pretty serious storm for you to get hail out of. So hail is formed through the ice accumulation cycles. It starts to fall, then it gets drafted back up, and every time it adds more ice, and it falls again, and they get bigger and bigger. Okay. Finally, all those updrafts. See, there's still some updrafts here going up, but you're beginning to drop some of this rain. All the updrafts have exhausted themselves, and it just rains out. The rest of it. Okay, so that's your final stage of the thunderstorm. Now, we called it thunderstorm, but we haven't said much about that. So let's talk about it. What makes thunder? What is thunder? Anybody? What's thunder? Second? All right, absolutely. You never have thunder unless there was a lightning strike somewhere. Thunder is a sound, okay? Sound is compressed air molecules, okay? What compressed the air molecules? A lightning strike. And guess what? You don't have lightning unless you have thunder, okay? Because it's always creating a really major disturbance. Okay? So the updraft, downdraft, circulating precipitation separate electrical charges. If you have the air mass moving up with water droplets in it and stuff like this, it's bumping into other things that are stationary, and electrons get knocked back and forth. Okay? Now, electrons, if they go to something else, that becomes a negative charge, but they always lost from something, so that becomes a positive charge. You don't create electrons. They come from somewhere. So anytime electrons move, one area becomes positive where it lost it, one area becomes negative where it gained the electrons. Okay? So the updrafts, downdrafts, all that motion and stuff, that produces separate electrical charges, creating charge sites. The charges accumulate in different parts of the thunder head. I think this illustration will show this. You have your updrafts and your downdrafts, and for some reason, this has become negatively charged, this and this have become positively charged. These areas have lost electrons in these areas, and when that happens, you have a problem, Houston, okay? Now, you can have multiple clouds out there too, and they may have similar or dissimilar charge distributions. This shows something awfully close to the same thing. Negatives here, positive here, and here. Okay? That's all been within. When these charge centers accumulate enough charge difference, then they discharge. Okay? And what that means is the electrons from here move to there. The electrons from here move to ground. The positive charges here, now don't think the rain has anything to do with this, it just happens to be here. But this, the positive charges here attract negative charges from the ground. And when that charge separation gets, the difference in charge gets big enough and the separation small enough, separation distance small enough, you can actually have ground to cloud lightning. Not just cloud to cloud or cloud to ground, you can have ground to cloud lightning. Now, I've seen one or two pictures before. I bet you there's some up there on YouTube if you know where to look for them that show somebody snapping a shot just as lightning is striking, and you see the lightning leaving the ground heading toward the sky. It is so bizarre because I always think of lightning coming from the clouds to the ground just like rain does. But it happens so fast you can't ever see where it initiated. But someone a few times have caught that, and you actually see the lightning going up, not coming down. Okay? And then, of course, cloud to cloud lightning again. These electrons discharge to these positive sites. Okay? So, the charges accumulate in different parts of the thunder head. The lightning is discharged between the charge centers. The discharge can be cloud to cloud, okay, cloud to ground, or ground to cloud. Any one of those. Now, when lightning strikes, that is an enormous transfer of energy. Huge transfer of energy. That's electrical charges just moving through space very quickly, and what always happens is you have a huge expansion from the heat from that of the pressure wave. And then you have a rarefaction that produces a sound wave. Every time lightning strikes, you get thunder. You may not hear it. You may see lightning way, way, way off in the distance and never hear it. That doesn't mean someone closer to that, they would have heard it, okay? You can hear, quite often, thunder and not see the lightning. That's just because you're in the shadow or something like that. But I guarantee you, if you heard thunder somewhere, there was lightning. So the expanding pressure wave from the heated air produces a crack of thunder, and then when it's over, you have a rarefaction where it goes back. That's what creates the thunder. You can't have lightning without thunder, and you can't have thunder without lightning. Now, I usually tell this little story at this time. There was one night when I was in the Navy. It was, we stood watches on the ship. I don't know where to start. Let's just start in the morning. There was an 8 to 12 watch, and then 12 to 4 watch. And later in the evening, there was a 4 to 8 watch. I'm sorry, an 8 to 12 watch at midnight, and then a mid-watch from midnight to 4 in the morning, and then 4 to 8 again. But over the evening hours, the 4 to 8 watch, they split that into 2 watches. They call it the dog watch, 2 2-hour watches. Because 6 o'clock, supper time, came right in the middle of that watch. If you're on watch, you'd have to wait so long, 2 hours to eat, or you have to eat 2 hours early. So what they did, they split that and called it the dog watch, okay? So you had a 4 to 6 and a 6 to 8. Now, I don't remember which one I was on. I know it was a dog watch. It was either right after supper or right before supper. And it was just unbelievable. We were out in the middle of the ocean. There was no other ship around us, nothing around us but water. But the clouds were just all over the sky, and it just looked like a spider web of lightning all 2 hours that I was out there. We just stood out and just were amazed by it. No other ships in sight. We just watched the lightning, and I've never seen it. It just continued just about all 2 hours, almost continuously solid, just lightning up, way, way, way up in the cloud. I don't know what caused that. I would have loved to have known what caused that. You could maybe hear a little rumble of thunder, but it was way high in the clouds. And it was just a network. I mean, just constantly happening. There had been a pretty major weather system. There was a lot of friction. And they were little discharges, not huge ones, so you didn't hear big claps. It was just constant. Just like the clouds had this neural network going on up there. It was absolutely amazing. Okay? Now, the next types of storms are our tornadoes. And these are pretty serious things. We talked about last time cyclones, which are tornadoes. Now we're going to talk about the specific event of having a tornado. These are the smallest. They are smaller than thunderstorms. Thunderstorms can sometimes be a huge band of heavy rain, and lightning and thunder. But a tornado is usually very, very focused. So it's the smallest, but it's the most violent weather disturbance you have. Okay? Not as much energy as a hurricane, but for that area, much more violent. More wind, a huge pressure drop is there. You don't want to be in one. ever, okay? What it is a rapidly whirling column of air, okay? The diameter can be from about 100 meters, which is about the length of a football field, approximately, to 400 meters, which is about a mile, okay? Wind speeds up to 480 kilometers per hour, which would be close to 300 miles per hour. 300 miles per hour, up to that, okay? Now, they say something close to a mile. I think that some of the ones that went through on, March or April 2011? 27, April 27th. I think that some of those that, I finally thought of the name of the town I was thinking of. I heard it on the radio, Phil Campbell. I don't know where Phil Campbell is, but there's a town that was just smashed by one of those tornadoes. Tuscaloosa was smashed, okay? Some of those were, I'm guessing, pushing more than a mile in width. I mean, just in diameter, okay? The damage produced by the high winds, the drop in pressure, okay, at the center, and also flying debris. That's why when we talked about our weather plan, get downstairs, because the flying debris, if a tornado came through, those limbs on that tree would just be snapped off like matchsticks, and some of them might come flying right through those windows. You don't want to be here. You don't want to be upstairs. You don't want to be in a room with windows. You don't want to be anywhere where that flying debris could smash you, okay? Now, they're often associated with intense thunderstorms. In fact, those thunderstorms having hail are sometimes some of the most likely to have the severe tornadoes. Now, we mentioned the drop in pressure. Anytime you have a spinning column of air, there's going to be almost always a low pressure in the center of that. That's what creates the spin. That's what creates the thing. You have air coming down very rapidly, and the bigger the drop of pressure, the more rapidly it comes. And the more rapidly it comes, the Coriolis effect kicks in and makes the spinning phenomenon happen. And you also have usually a big change of temperature. And when that happens, then you have one column of air moving up and one moving down. The more rapidly they're going, the more rapid that spin can be, and those can be intense. And that's often associated with the thunderstorms. Okay? Here's a picture of one. And boy, if that's not more than a mile wide, I don't know what is now. That picture's no longer in the book. One that's in the book was at Marquette, Kansas, and if I'm not mistaken, that occurred a few months after the ones that did here. I think Marquette, Kansas got really whammed too. Probably just about as bad as any town in Alabama, but it wasn't the whole state getting knocked as it was in Alabama. If I'm not mistaken, we kept power for a while during that, and the weather people were saying, look, there's tornadoes all over the state. We're only going to focus on the biggest, the most powerful, the ones closest to us. We can't worry about the others because we got to deal with the ones closest, because there were category 1s, 2s they weren't even mentioning, 3s, 4s they weren't even mentioning. It was only the 4s and 5s that were getting a lot of attention. Do they have a category 6? I don't remember. I don't think they do. But it's...
that town you were just talking about, Phil Campbell, they got hit by that tornado.
Yeah.
In town in Franklin County.
Franklin County, and where's that? Northeast? Northwest?
Figuring it out now.
Okay. And there was another town that got smashed too. I just can't remember its name. It either started with a P or started with a C, because I always got it crossed up.
Concord?
Well, it may have been, but I thought it was a bigger name than that. But I know Concord got hit really badly too.
Yeah, Franklin County, that's out near Florence.
Florence, okay, northwest.
And like when you're headed into, like on the northeast, probably say northwest, heading into, heading into northern Mississippi.
Right, exactly. Okay. So, boy, you don't want to be anywhere near one. And if you hear the siren, you go down. You get down, low level, interior space, and hang tight. Several years before that ban, there was, I think it was in Piedmont, Alabama, there was a tornado that hit. And it seems like it was a Friday afternoon, I believe it was Piedmont, and it hit a school in the area, and some of the students were doing absolutely correctly, positively exactly what they were supposed to do. They were in a gym, so they couldn't get into a small interior space, but and that tornado knocked the wall over on top of them, and I think a few of them got either very severely injured or possibly even died, even though they were doing exactly what they were supposed to do. There was no basement in it, so the lowest level, interior, wall, everything that should have been providing strength, it got knocked over anyway. When these things hit, there's nothing to stop it. I mean, the pictures I remember seeing of Phil Campbell, there was some big industry right in the middle of town. It just looked like a parking lot afterwards. I mean, things were strewn everywhere. The building you couldn't even see but pieces of the building, and they were all scattered everywhere. Okay. They're tough things. Now, in our text, they show a picture of a hailstone, and this one was in Iowa, and I am trying to read their scale. It looks like it's about close to 4 inches in its long dimension. That's one big chunk of ice. Okay? Now, when those hit, cars get damaged big time. Dented, paint jobs destroyed. Yeah, you're in serious money there. That's not the worst of it. Okay? Roofs get damaged. Major. People have to have, whole neighborhoods have to have the roofs replaced, okay? But growing up on a farm, crops, and these happen quite often in the springtime when crops are young, just getting going, and hailstones hit it, they wipe out the plant, period. I can remember a few years when the peach crop has been damaged severely by hailstone. I love my peaches in the summertime, and when a hailstone hits a peach, it gets bruised so badly it's never going to develop properly. Probably it's going to rot on the tree. Bad news. But they show that picture in the text, not on the slide set. Okay. Now, there is a table that's given that talks about tornado damage. And they don't show this on the slide set. I thought they did, but I think it may have used to been right there, and it isn't there anymore. But let's just go through this. And it only goes up to Category 5. That's what I was thinking it was. But they also have another category they call Category 0 storm. So there are 6 categories, but it's 0, 1, 2, 3, 4, and 5. Now, and this is based mostly on damage or potential damage, but it's also on wind speed. They don't usually take the barometric pressure in a tornado. They just happen so quickly, rapidly, no one's there to take it, and no one wants to be there to take it. The Category 0 tornado, light damage, winds under 120 kilometers per hour, which is 75 miles per hour. That's still pretty strong wind, folks. Damage to chimneys, tree limbs broken, small trees pushed over, signs damaged. A lot can happen in the Category 0. Now, one swept through our farm. I was over here in Alabama, so I didn't get to see it or the immediate damage from it. But it swept through our farm, and it was incredible the amount of damage it did, and it was a Category 0 tornado. That's at least what they classified it. I can't help but think it was great. It should have been. It was more than that, especially when it went through our farm, because you can still see to this day, and this was years ago, a big, wide swath of where there are no trees and where it was just pretty dense trees, just wiped them slick. I mean, just took out the whole, it was my mother's front yard. You know, on the one side of the driveway was just wooded area. And now it's cleared area because it took them out. And they were not small trees either. They weren't huge trees, but they were not, you know, the way it makes it sound here, small trees pushed over. These were substantial trees pushed over, okay? You don't want to mess with that. Now, there's sort of a bizarre story with that one. My younger brother had 3 children. The oldest daughter had been at law school at Vanderbilt, and she had met this guy, and they were dating pretty seriously, and I think by this time they had gotten engaged. Yeah, I'm pretty sure they had, because this was the time when they were exchanging families, basically, is what I call it. His family came down to Georgia. He was from Columbus, Ohio. That was where he grew up. His dad was actually the chairman of the Children's Hospital, the chairman of the Department of Pediatrics at the big Ohio State University Medical School. So, a pretty impressive dude, I mean. And his son was marrying the farmer's daughter. Okay, my younger brother is an electrical engineer, worked at an electric power company, but his passion was farming. So he lived out on the farm. You know, it was a small house, you know, but adequate. Things were not, I mean, it had to be night and day for them. So they came down to Georgia to meet the parents, okay? And Dan knew there was supposed to be weather that day, so he wanted to get them out there to see the farm before the storm came up. So he had them out probably in trucks, which was probably a unique experience for them, driving through the pasture, looking at the cows and stuff like this, and things felt like it was changing. They looked across the farm that's adjacent to ours. It's an old dairy farm. No one operates it anymore. And they saw a tornado making its way across the field. And they immediately got out of the vehicles, which was the thing to do, and down into a ditch. So here, the chairman of the Department of Pediatrics, head doctor in the Children's Hospital in Ohio, Columbus, Ohio, capital of the state. He and his wife and son were down in the ditch on the farm trying to keep from getting swept away by the tornado. It was just remarkable to me. They weren't on the next plane back to Columbus. Forget the wedding. We don't want to have anything to do with these folks, but they carried it through. They were real troopers. But that tornado came through. My older brother and his wife had been living in that dairy up until like a few weeks before that in the what they called the big house. It was a big, nice, old 2-story house. Had been owned by the Winners, and the road was named Winter Road. They were the big farmers on that road, and the Boyces had bought it, and Mrs. Boyce had really fixed it up nicely, but she had gotten old and sick, and she had died just a little time before that. So Mike and his wife were being kicked out of the house by the brother, who actually inherited the house, but he didn't want to take care of his mom, so Mike's wife, being a nurse, and Mike were living in the house taking care of Mrs. Boyce. When she died, they got booted out, so they had just moved like a couple weeks before. And when that tornado came through, no one was living there then. It actually twisted that big, old, solid house on its foundation. I mean, just amazing. Okay? Now, then it cut that swath of trees out. It went by and took the top, a portion, maybe about a third out of a big magnolia tree on one side of my mom's house, swung around the house, wiped out the block building we had in the back where my father had his shop. He was dead by now, but had his shop, big, substantial cement block building. Hardly one block was left on top of the other. Okay, ripped the top off of the shed, just completely tore the shed apart. They found parts of the roof almost a half mile down in the woods later. There were some parts they never found. This was a Category 0 tornado. It did all that damage, but somehow had swung around my mom's house and had just taken off a couple shingles and twisted one post a little bit. And she was inside, and she said, boy, that was some storm that came through. She didn't even realize it was a tornado had happened. So it's just so bizarre how they move and work. Now, what I was going to say, I'm still on tornadoes, am I not? Yeah, because I was doing this. I meant to say it here. When they say a drop in pressure, I mentioned that it's a huge drop in pressure. When you see a tornado pass through, what is typically the situation that you see where the houses were? Typically, the houses aren't blown down, the roofs are taken off. Okay? That's why there's so much that, because the low pressure actually sucks the roof off the house. Literally takes the roof, picks it up off the house, and sends it somewhere else. It did that to the shed, it did that to my dad's shop. It was just annihilated. Okay? So that's what's happening. The low pressure actually pulls the roof off. So when they're talking about, when they're doing building, and we built our house over there, we had them put in what they call hurricane trusses type thing, to extra strong joints there to keep the roof in place in case there was severe wind. Okay, so that's the Category 0. Talked way too much about that. Category 1, moderate damage. Winds, I'm just going to give it in miles per hour, 76 to 112 miles per hour. Roofing materials are removed, okay, not just damaged, but removed, sucked up and blown away. Mobile homes and moving automobiles pushed around, overturned. Boy, after that string of tornadoes that went through here, we had have a lake place up on Smith Lake between Arley and Houston, Alabama. And so we went up that next weekend to see if there was any damage there. It was unbelievable. Let's see, actually we made 2 trips close together. I guess that one was first. We went through paths where some of those tornadoes had gone through. The one that went through Huntsville, we went through its path. There was one place, I think it's strict leasing. You know, they lease the tractor-trailer trucks, or at least the trailer parts of them. And there was this place that had a whole bunch of them sitting there, and it looked like someone had played dominoes with those trailers. They were just tossed all over the place. I don't know how much damage that company suffered, but I mean, they were just lying all over the place, knocked each other off. It was amazing. Okay. Category 2, considerable damage, winds 113 to 155 miles per hour. Roofs torn off the homes, sucked off the homes. Mobile homes demolished. Boxcars overturned. Large trees snapped or uprooted. Light objects become missiles. That's what you want to avoid if we hear the siren. Get downstairs. Okay? Category 3, 156 to 205 mile per hour winds. Severe damage. Roofs and some walls torn off houses. Whole trains overturned. Most trees are completely uprooted. Cars lifted off the ground and thrown around like nobody's business. I don't know if any of you saw that movie Twister. I didn't, but I saw the whatever they call the trailers for it. And they had cows being thrown around. And that can easily happen. And that would be scary to see a cow zoom by, you know. Poor cow. It would be terrible for her, but, you know, whatever. Okay, Category 4, devastating damage. winds 206 to 260 miles per hour. Homes are leveled, cars are thrown, large missiles are generated. You don't want to be anywhere near one of those. There's no safe place generally for that. Get as safe as you can, but that's it. And Category 5, this is incredible damage, 261 to 318 mile an hour winds. I can't even imagine that, okay? Homes demolished, swept away, automobile-sized missiles flying through the air more than 100 yards, trees not just thrown up, the bark is taken off the trees, okay? Big businesses, like we talked about in Phil Campbell, they're demolished. I mean, there's nothing left. It's just floor space. That's all. It's unbelievable what damage these things can cause, okay? So, now we're back on hurricanes. Now, what is a hurricane? Ask the people in North Carolina. It's a lot of things. They usually start as a tropical depression. Why tropical? They're in the warmest band of the oceans, okay? In the Atlantic, that usually starts off the coast of Africa, and that band right along the equator between the Tropic of Capricorn and the Tropic of Cancer, that band along there, anywhere in there, they could be started. Tropical depression, the reason they call it depression, an area of low pressure, depression, depression, low pressure. The winds are generally moving about 55 kilometers per hour, which would be in the low 40s miles an hour, okay? Not too severe, but the winds are moving. They're usually circular flow, so that's happening. If they build up strength, now two things are happening. Your pressure is dropping, and as the pressure drops, the wind speed increases. So the winds increase to 56 to 120 kilometers per hour, which would be on the neighborhood of 72 miles per hour. Okay? That's a tropical storm. Okay? Now, they haven't said much yet about this, but by the time a tropical depression quite often has rain, like a low pressure area. Okay? A tropical storm almost always is drenching rain. A hurricane, very, very low pressure. Okay? Winds excess of 120 kilometers per hour, which is excess of, I think, 75 miles an hour. Fully developed hurricane has a calm eye surrounded by intense rain and thunderstorms. And when I say intense, I really mean intense. I have actually seen pictures taken from inside the eye, which is perfectly calm. I mean, no wind at all. Okay? And yet, you can see this wall of wind whipping past you. I mean, some distance from you. And it's just unbelievable. Okay? Inside that eye, that's where your pressure is the lowest. I can't remember if I told you all this or not. I had a friend when I was doing my master's at the University of Georgia. He was an undergraduate. He happened to be a forestry major. But when he finished, by the time he finished his degree, he decided he really wanted to fly. Well, his dad was a pilot for Eastern Airlines at the time, I think it was, and that's before they went out of business. But it was one of the biggest airlines in the country, but it went out of business. I think his dad went on with Delta then, I believe. But there was a lot of storminess in the airplane industry at the time. But Doug had decided he really wanted to fly too. So after he graduated with his degree, he started his training. He had already, I think, had his license. He started his training to get into bigger and bigger aircraft. But at the time, like I said, several of the airlines were going out of business. TWA, Pan American, Eastern, Braniff, Ozark. Many of those airlines were going out of business in that time frame. So there weren't a lot of jobs available. So he got a job as a hurricane pilot. And what he would do, he would take the aircraft that had all this instrumentation, things like a big passenger aircraft, but it not have any passengers, be full of equipment, and pretty sensitive equipment that would go in and measure pressures and wind speeds and temperatures and all sorts of things, had all these ways to do this. And he would fly really high over the wall of the hurricane. I'm sure that it was really rough going up there, and then drop into the eye and go down into the eye. Now, they'd have to be big enough hurricanes to have a big jet plane inside, but that had to be incredible. And he'd stay in there probably a few hours and stuff, getting collected. He had scientists or meteorologists on board taking all the stuff, and then when they're ready to go, then he flies out of that and over the top and back home again with all this data that they've collected. But that calm eye, that's where they would go. But boy, it took a lot to get there. Went way high to try to get over most of the storm, but even then it had to be terribly rough going. Okay. Here is one picture. The one in the text is a different one. And in the northern hemisphere, just like every low pressure area, the winds go in a counterclockwise direction. In the southern hemisphere, they go in a clockwise direction. I think I told you all the story already of my physics professor at Georgia Tech who went down to meetings in Buenos Aires, I believe it was. I told you all that one? Yeah. He couldn't wait to go flush the toilet, in the party city of the southern hemisphere, and he went to flush the toilet, because it's a strange animals. But you see here, you can see that counterclockwise flow here. There's the eye, right in the center, perfectly calm, right around the center. Intense winds. That's when the winds are at the strongest. Right past where the compass is. It's just unbelievable. Okay? Here is a diagram showing what's happening during the formation and when it's at its peak. Again, we have low pressure in the center, so you have winds rushing in to fill that low pressure. Rushing downward with the spin of the earth, that's what creates the motion. Okay? The circular flow. They rush down, and in this, it's usually cool, dense air rushing down in the middle of this warm, hot, tropical moisture, and it gets sucked up as the others do, and hauls it off. And these are spinning like crazy, rain like crazy here. In the eye, no rain, no clouds overhead. But around there, intense rainfall coming down in sheets, spinning from the Coriolis effect, and it just is moving on. Now, what it's doing is sucking up hot air off the ocean. And that hot air is providing more energy for the storm. So most of the time when they're over open water, warm waters, as long as there's not anything interfering with it, they're growing in strength. And remember, oh goodness, what's the last one that just went through North Carolina?
Hurricane Florence.
Florence, okay. When Florence was out over the ocean, she got up to at least a Category 4 and possibly got close to being a 5. I don't know if she did or not. But then when she got closer to the shore, she started losing speed. She was moving so slowly that she got to being batted around by cooler water and stuff. So she lost strength, but boy, she was still so big, so much tropical moisture. Now, I was in a book study at our church, and there was just general talking going on there of people saying they didn't know why God allowed, hurricanes to come and just do so much damage and kill people and stuff like this. Why is that true? And it just happened to be that Jerry Tracy was in that same book study that night. I only went that one night. I don't know if he stayed with it or not. And he said, well, actually, that's part of nature. He said, if we did not have hurricanes to take the energy that exists around the equators and move some of that heat and temperature up into the temperate regions, these areas would get way too hot, and these areas would be way too cold. He said, we've got to have hurricanes to transfer that energy. And that's their job, and that's what they do. They transfer it. Unfortunately, they dropped it over North Carolina, but it's going to land somewhere, and all that rain and the wind and everything else. So the maximum winds are in the what they call the eye wall, right on either side. Hurricane winds extend out a certain distance here, and then gale winds, which are usually tropical storm type winds, out here. Now, I don't know if y'all remember Ivan. That happened many years before 2011 when we had the really major storms then. But Ivan hit the Gulf of Mexico or was in the Gulf of Mexico and hit the Alabama coast, Gulf shores and those type areas, and came up into central Alabama, and it was still a tropical storm when it reached Birmingham. It was a major, major hurricane down when it hit the coast and came all the way to Birmingham. It was still a tropical storm. We lost power big time. We had a friend of ours was living down on, what's that island? Is it Sapelo Island off Mobile?
Working
Bay.
At Mobile Bay.
Off Mobile Bay, right. There's an island down there. I think it's Sapelo. I'm not sure, but I believe that's it. She was with the Food and Drug Administration. They have a big lab down there, and it was heading right toward them. So she got in their car and brought a friend with her. They drove up to think it would be safe in Birmingham. And it was safe, but we lost power within minutes of them getting to our house. And but we were able to make it. It was pleasant weather and stuff, temperature-wise, so we didn't suffer too much in it. And we had gas stovetop so we could eat well and everything. So we were fine. Later she found out her home at Sapelo got less damage than we did. We had one pecan tree that lost a few limbs and that kind of stuff, but her house was less damaged than ours was. Our house wasn't damaged, but her area. So they do strange things too. Okay. Now, they also skip the hurricane ratings. Okay? And I want to do this because they're on opposite pages of each other, looking at the difference between the hurricane and tornadoes. Hurricanes also have 5 classifications, categories. Remember, tornadoes have 6, but they start at 0 up to 5. Hurricanes start at 1 and go up to 5, so there's 1 less. So the hurricane category 1 is 75 to 95 mile per hour wind. The tornado category 0 is winds under 75 miles per hour. Okay, so that started. So category 1s are 76 to 112 tornadoes, 76 to 95, 75 to 95 hurricanes. Category 2, which are called moderate hurricanes, are 96 to 110 miles per hour. Well, that's the upper part of Category 1, tornado. Okay, that's Category 2, hurricane. Category 3 is extensive damage, and that's 111 to 130 miles per hour winds. That would be basically a low-speed Category 2 tornado. Category 4, hurricane, extreme hurricane, is 131 to 155 miles per hour. That's the upper limit of a Category 2 tornado, okay, for wind speed. Category 5, catastrophic hurricane, over 155 miles per hour. That basically is a Category 3 tornado. Okay. Now, of course, a Category 3 tornado is not going to have as much energy, but the wind speed is still going to be as much. It's just isolated to a very small area, but that very small area is going to get clobbered. And then you still got Category 4 and 5 tornadoes to go that are way stronger than the winds you'll see in a Category 5 hurricane. So you see, tornadoes are so intense, but they're a pretty small area most of the time. But that April, when they went across Alabama, some of them were on the ground for miles and miles and hardly seemed to lose much strength at all. That was unbelievable. We got to go to the weather center for our field trip. I can't remember if it was the next summer or the next fall, but we got to go to Channel 13. And Jerry Tracy told us now he had a video and everything showing much of what happened that day. Someone had put that together there at the station. And he said that the weather people themselves have a little, they don't ever talk about it, it's just their little algorithm, you might say, of predicting how bad the storm's going to be. They collect data from way up high, they collect temperatures, winds, and other things, and different indicators. Sometimes you can have perfect conditions for a severe tornado on the ground, but if the upper winds are doing something else, it's not going to happen. Or you could have really huge spinning stuff out there, but if the ground area is not cooperating, you're not going to have the tornado. He said they have sort of a scale, and I wish I could remember the numbers on the scale. I think he said anything greater than 100 or 120, you were expecting really bad tornadic activity. He said that day, when they came in and started looking at the data, it was way over 400 or something like that. I may have the scale wrong. He said no one had even heard of that kind of a number. And they didn't know what to expect. They just knew it was going to be bad. Really, really bad. And that's why it was such a broad range all up and down the whole state of Alabama, and such long duration, intense storms. It was amazing. Later that summer, I think it was, we were going for some reason down to either New Orleans or South Mississippi or somewhere, and we could drive on the interstate and you could just see the bands where the trees had been just disrupted, just almost not quite a mile wide or so. Just we passed through one after another, where the different tornadoes just swept up and just wiped out forest. Amazing. All right, now we get to weather forecasting, and this is what Jerry Tracy and his ilk do in weather forecasting. And frankly, what it sounds like here, I'll say this: they do a much better job than they did in the old days. But even with that, there's big limitations. Now, to forecast the weather is based on these mathematical models of the atmosphere. And you'll hear Jerry sometimes say, it seems like James Spann says it all the time, well, the RPM model, the this model, the that model, but this model says this. Because they have different ones of these models. The National Weather Center, the different groups will have different models. And some will say one thing and some will say the other. Well, why? Because think of what our atmosphere is. It goes for miles and miles and miles up and covers the whole globe, right? Okay, so even in a particular area, you've got a lot of things to do. Well, how do they measure that? Well, a lot of aircraft that are flying around there are collecting data from the atmosphere, and they send it back, some of them to the National Weather Center or the Hurricane Center or whatever. They send up balloons, I think maybe 3 times a week, to collect data. You know, they have devices that are being hauled up by the balloons, wind speed, temperature, moisture, that kind of stuff. You're modeling an entire atmosphere with balloons 3 times a week and a few aircraft data. How in the world are you going to model something as big as the atmosphere with that? You're limited, very limited. But even as it is, the calculations they get from just this limited amount of data, there are billions of calculations you make with it, and there's no computer that can do that except the supercomputers, like the one up in Huntsville. What is that? A Cray or McCray or something like that, supercomputer. Those are required to do this, and still they can't do a great job. Limited input, but also covering such a big area. Even with limited input, they have to make billions of calculations just on those little bit of data they have. They're fairly accurate forecasts up to about 3 days if possible. So what is a 7-day forecast? It's good guesswork. Okay. 3 days, fairly accurate. Anything past 3 days, well, basically, what do you do? 7 days out, and they say, oh yeah, I know exactly it's going to be. Well, by the time that time comes along, you're looking at 7 days further out, and you forget, hey, today is no more like they said it was 7 days ago, but who would remember that? Unless you had big plans that day, like an outdoor wedding or something, which we're supposed to be going to tomorrow. Good luck with that. It's almost impossible. If you're trying to predict even 7 days out, you might think, oh, it's going to be a beautiful day, but by the time that 7 days gets there, is passed, they probably changed it 2 or 3 times, and who knows what you got. Now, here's the major uncertainty. Insufficient technology to connect the small scale to the large scale events. Okay? Small scale to large scale events. What's those criteria that they use to predict tornadoes? That was covering miles of vertical range, probably miles of horizontal range. You just don't have, number one, the data to collect all that, nor do you have ability to calculate that much data, and then to connect the small scale events to the large scale events. That's a hard thing to do. And here's the thing. Ultimately, the oceanic influences need to be better understood. Okay? I think I've said this before in this class, I think I've read and heard this said before, in some senses we know more about outer space than we do about our own oceans, because they're so vast. There are so many things going on. The next chapter we're going to be talking about some of these variations within the oceans. We don't understand what's driving forces there. Okay, there's a lot of stuff we need to understand better, and we just are at the tip of it. Now, near the end of this chapter, there's going to be a blurb on El Nino. Now, I don't know why they put it that way rather than right here. El Nino is one event. I don't think they understand it well. This is one of these things. They recognize it when it's happening, but it's almost impossible to predict. It's a lot like volcanoes, okay? You know that something's going to happen one of these days, or one of these years, or one of these decades. You just don't know which decade it's going to be, Same thing through here. We don't understand what causes these things, why they happen, but we know when they happen, they're going to cause a lot of other things. So El Nino is one of those. We pretty much have figured out when an El Nino occurs for the next couple of years, year and a half, something like that, it's going to be major changes in weather somewhere fairly close, okay, to El Nino. Further away, it's still going to have influence. Why that's happening, we don't know. The opposite of El Nino is something called La Niña. El Nino is the little boy, is what that means. I don't know why they call it that. And La Niña is a little girl, or something like that. I don't know my Spanish, so something like that. It's off the coast of South America is where it occurs, and it has major influence on our weather. Okay? It's an oceanic situation, and we don't know why it happens. We don't know. We can't predict too much why it happens. When it's going to happen, we can say, well, we think it's going to happen in the next few years, but we can't specify which year because it follows sort of a cyclic pattern. So just based on past, we know it's going to happen, but why, we don't know. We certainly don't understand those oceanic influences. All right. That was the first half of the chapter, and that was the weather part. Now we're into the climate part. What's the difference between weather and climate? Any ideas, suggestions?
I can never figure that out.
Okay. Well, here's the thing. Weather is what's happening now. Temperature, rainfall, humidity, that kind of stuff, that's what's happening any day, any place. That's what's occurring. Okay. Sun shining, warming things up. It was raining just a few minutes ago. That's the weather. Okay. Climate is what's happened over the long haul. Okay. The climate in the southeastern U.S. for many years has been warm, moist environment, blah, blah, yeah. Whereas the climate in the Midwest is much drier, much more extreme in temperatures, blah, blah. In the deserts, for so many decades or centuries or whatever, been dry, and that's climate. It's the composite, larger weather patterns occurring over a number of years. That's what we mean by climate. Not what's happening today as opposed to yesterday or tomorrow or last week or last month. It's years of a pattern. Weather patterns occurring over a number of years. The climate is a determining factor in what types of plants and animals are at a given location. Okay? We have huge, if it was left to its own devices, we would have huge hardwood forests. That would be our climax forest. That would be the forest we would expect to have. Of course, we clear forests and farmland. Or we clear farmland and plant pine trees, because pine trees grow fast and sell. But natively, we would be hardwood forests. That would surround us, because we have so much moisture, so much warm weather, we would have a great crop of hardwood forest. The animals at a given location. Now, this is something that, in my lifetime, I have seen changes happen. When I was living in Nebraska, they were beginning to sight the first armadillos they'd ever seen on the highways of Nebraska. And when I was growing up, I don't even remember armadillos in Georgia, okay? But now you see armadillos all the time. They used to be way south in the desert, Mexico, Texas, those kinds of areas. That's where you saw armadillos. Now you see them up as far as Nebraska, okay? Not in huge numbers, but you never used to see them at all. We have beef cattle over in Georgia, okay? We're selling the second herd. Younger brother is getting tired of farming and wanting to enjoy his retirement. So, but one of the most beautiful things that we never had this growing up, cattle egrets. Big white birds that hang around the cattle. Never had them when I was growing up. Only after I went off to college or in the Navy or sometime, when I come home, I'd see these flocks of birds around the cattle. I thought, what in the world are those? Cattle eaters. And they're really beneficial. They hang around the herds. They love to eat the flies and stuff that bother the cattle. So they're really doing a good job. But never saw them before. Okay? In the pastures around the house we built over there are now thistles that we never used to see. That's another type of plant. I don't know where they came from. My older brother has a few ideas, but there's just different things are changing. But climate is the thing that determines that. The type of houses built. If you look around this campus, what you notice about just about every building on this campus. This building, almost every building, one building on this campus that doesn't have a flat roof. I don't think flat roofs are good ideas, period, but you can get by with them in the South. Okay? It's a lot cheaper to cover a flat roof than it is a steep roof. Because here you're covering the same area, but now you've got to go up and down both, So they build them cheap. And so they have flat roofs on every building except, what is it called? Jesselyn building, right next to the alcohol building. It had to go through a major renovation. Its roof had been leaking so badly, they went on and put a tilted roof. In fact, a metal roof on it. On the Birmingham West Campus, that new building is the only one that has a tilted roof. On the East Campus, I don't think there's a single building. They build them cheap, Could you do that in the Northeast, in the far West, in the Himalayas? No, because in the wintertime, snow would cave in. We never get enough snow for a flat roof to have any problem at all. But in those areas, in fact, in the Alps, they make those A-frame buildings really, really steep so the snow will slide on down and not accumulate. If you had them like this, you crash them in. So yeah, the type of houses built. We can get by with what we call crawl space houses. That's what we have. Partial crawl space that we live in here, the one at the lake and over in Georgia. Crawl space houses, okay? They don't do those up north. All their pipes would freeze, okay? Our crawl spaces never get cold enough for pipes to freeze. Maybe the outside pipes might, but not in the crawl spaces. So yeah, type of houses built. Up there they have basements, got to almost. But down in New Orleans, you never see a basement. It would be flooded if you had a basement, okay? So the types of houses built, that's the determining factor was climate. Lifestyles, okay? Why do you reckon Alabama, Florida, and Texas typically have such good football teams? Mississippi, Louisiana, Tennessee. Well, we have this climate that kids can get out and play football all winter long. There's no problem. Whereas up north, they ice skate. We don't have any good hockey teams down here, do we? No, because there's never any ice, okay? Kids don't grow up knowing how to skate. So our lifestyles are very different, okay? Determined by the climate. Well, climate also influences things, like the shape of a landscape, okay? If you have huge amounts of winds, you're going to have ventifacts. We talked about that in an earlier chapter. Huge amounts of snow buildup. That's going to shape the landscape. Sandstorms. I have a niece and her husband and 2 kids, great nephew and niece, are living in Dubai now for 3 years. They've been there a little over a year. They'll be there for about 2 more. They have sandstorms that you just don't get out. You do not go out when there's a sandstorm. You try to keep all your equipment and cars and everything else out of those sandstorms. Okay? So yeah, that shapes the landscape. The types of soil. I think I've mentioned this before. Midwest, most of your far northern soils, pretty deep, rich soils. Part of the reason for that, half the year there's no chemical activity going on in those soils. You don't have losing organic matter. Here in the southeast, we lose organic matter every month of the year. I mean, remember I gave that little rule of thumb of anything below 40 degrees Fahrenheit usually is not going to have a lot of chemical activity, chemical breakdown of materials in the soil. And for every 10 degrees you get above 40 degrees, your chemical activity doubles. Well, guess what? The coldest month of the year, you're probably going to have at least half of your days more than 50, a high more than 50 degrees in the south, right? So we lose organic matter all year long. So our soils are pretty low productivity soils, okay? Agricultural type and productivity goes right along with that. Except for this. Those rich, rich soils up in Iowa and those areas, okay? they don't get their spring thaw early enough, and nowadays with global warming, they don't have any problems with this, but in the past, if they didn't get that spring thaw early enough, then they can't get into the field to get the soil ready, and they can't get the crops in on time, or if it starts raining right after that fall, and they can't get in the fields on time, they have such a short growing season, they may not make the crop that year. And if they don't, whoa, they're in serious problem. Whereas here, when my father was farming, he didn't do this on all his fields because we couldn't afford to, our land wasn't that good, but he double cropped where he planted his wheat and other small grains in the wintertime, harvested those in May, then followed them up with soybeans, and would get a soybean crop and harvest that by October, November. Okay? No problem. Never a problem. He double cropped, not every field, but just certain fields just about every year, where they can't do that at all up north. Even though they have all that rich soil, they can't, some years can't get a single crop in if the spring thaw goes too late or the fall freeze comes too early. They may lose a big portion of the crop, especially if that spring thaw is followed by a very wet spring. They can't get in the fields to get the land ready. So yeah, climate matters. Okay? Now, what are the major climate groups? Okay? Two primary factors. Okay? Both of these have to do with sun. Okay? One is the intensity of the incoming solar radiation. Now, we talked about this in the earlier chapters. We're coming back to it now. This is a big. Okay? Sarah's going to be the sun for us today. She's real bright. Right. Okay. Now, here's the globe. This is about right for this time of year. You're just past what happened last weekend. Vernal. First day of fall. Fall. Vernal equinox. We talked about that earlier. We mostly did spring equinox, but vernal equinox. Okay, we went from our summer to our fall. Okay? Now, that's about where we are now. Sarah's rays are coming in, hitting right around here, the strongest. Glancing off up here, glancing off down here, very cold, intensely hot, and moderate. Okay? Going around here, rays are hitting right here, intensely hot, frigidly cold, not quite as cold down here, moderate. Cold but moderate, warmer but moderate. Okay? Move all around there, back, similar to what it was here. Move this way, very intensely hot, pretty hot, cold, incredibly cold, the intensity of the incoming solar radiation, that's the big one, okay? It's determined by the angle of incidence. The problem isn't how far you are from the sun, it's where the sun rays are coming in. Everywhere near the equator, they're coming in almost 90 degrees year round. All year round, okay? This time of year, they're coming in sort of direct to us, a little bit more of an angle. In the wintertime, even more of an angle. That's why we get colder in the wintertime. Less in the spring, coming in very direct, not quite like equatorial, but fairly direct in the summertime. That's why we're so hot in the summertime. Okay? So it's that angle of incidence coming in. Never a good angle of incidence at the polar regions. So they're always cold. Sometimes colder than others, but always cold. So that's the number one. Number two is number of daylight hours. Okay? Now around the equator, 12 and 12, 12 and 12, 12 and 12, or pretty close to that. Now, everywhere on the globe, 12 and 12, 12 and 12, 12 and 12 now, because we just passed vernal equinox. But have you noticed already? I'm noticing big time that when I get up in the morning, it's still pretty dark, okay? Whereas this summer, I get up, it'd be a little razor light, you know? Now, not, okay? I don't want to get out of bed. And guess what? Before they take off this dumb daylight saving time, it's going to be so dark. You know, I'm not going to want to crawl out of that at all, okay? It's going to be so dark outside. When you finally do take it off, it's still not going to make a lot of difference with the next summer, okay? Because the number of daylight hours are going to decrease until 21 December. Finally going to start increasing again. So number of daylight hours, that's going to be another big factor, okay, in our climate. The other thing, another contributor to that, because it has to do with the tilt, the angle of incidence is how much we're tilted. Here's this 23.5 degrees. See, this is level, okay, and this is 23.5 degrees from straight up, okay. So that's so in other words, your equator is 23.5 degrees from the horizontal, okay. So the tilt of the Earth's rotational axis, the equatorial regions receive more direct solar radiation at a stronger angle, a more like 90-degree angle. The intensity changes on a yearly basis. Not so much in the equatorial region. This belongs in the temperate region, and the number of daylight hours vary annually. And again, that's more not the equatorial region. This should be a separate bullet. These two should be another separate bullet. This is for the anything other than equatorial region. Okay? Make sense? All right. And then we have climate and latitude. We've already been talking about that. At the low latitudes, that means the latitudes 0 to, say, 20 or so, north or south, you have high solar radiation because it's coming at a direct angle. Yearly variation of temperature very small. Temperature is uniformly warm, okay? Uniformly warm. That's the tropical regions, basically between the tropics of Capricorn and the tropics of Cancer, okay? South to north of the equator. Then you have your middle latitudes, okay? That would be north of the tropics but south of the Arctic. South of the tropics but north of the Antarctic, okay? Those are your middle latitudes. Here you have higher solar radiation during one part of the year, like in the summertime when we're tilted toward the sun, and lower when we're tilted away from the sun, which is coming up soon, okay, in the next few months, okay? Overall temperature is lower than it is in the lower latitudes, but greater variation than in the low latitudes. See, in the low latitudes, for instance, Hawaii, I've heard people talk about it. 70 degrees just about all year long, okay? And the hottest part, it'll get up a little above 80, okay? And the coolest part, it may drop down into the 40s or 50s. But very little variation. I don't know if it ever gets in the 40s, really, but very little variation. In the middle latitudes, 100 plus in the daytime, in the summertime, minus, not often minus Fahrenheit, but minus Celsius in the wintertime, okay? So you have more variation than you have in the low latitude, but the overall the temperatures on average are lower. The high latitudes, at the polar regions, the maximum amount of radiation during one part of the year and absolutely none at the other part of the year. But even when it's at its max, it's not as much as it is in the other areas. So even when it's tilted like this, most of the direct radiation is toward the low latitudes and the middle latitudes. This is still at a really low angle of incidence, so you don't get much. But it's much more than they're getting down here, which is absolutely not, because there is a shadow then. So yeah, some parts of the year, absolutely no radiation at all. Okay? Overall, the temperatures are by far the lowest, but with also the widest variation. That variation isn't coming from the high end, it's coming from the low end. I don't know, I think they get into the minus 45s or so in the coldest part, and in the warmest part, they might get into the 40s, occasionally. That's a huge, huge, huge variation. Not on the upper end, but on the lower end. Here we have large variation, say 0 to 100, that's Fahrenheit. That's 100 degrees. There's much, much wider. Okay. All right. Here's the pictorial exhibit of that. Always, the low latitudes are getting very direct radiation. Okay? Very direct radiation. Even when it glances very little. In the middle latitudes, you see there's more of a glancing glow there. We never get the direct radiation they do here. Even when we're tilted toward the sun, we don't get as much as they do here. In the polar region, the high latitudes, look at that angle. Never any direct radiation, always at an angle, and part of the year, absolutely none whatsoever. So it's just incredibly different. And what are the lines of demarcation? Tropic of Capricorn, minus 23.5 or 23.5 degrees south, to the Tropic of Cancer, 23.5 degrees north. That defines the tropic, the low latitudes. The equator, of course, is right at 0. That's why they call it low latitude, low numbers. The polar areas are above 66.5 degrees north and 66.5 degrees south. They're to 90 degrees north and south. Very high numbers, very low, high latitude, very low incident radiation. Some parts of the year, none whatsoever. Anything above the Arctic Circle or below the Antarctic Circle, there will be at least one day of the year you get absolutely no sunlight at all. And the further north you are, the more days of the year it'll be with no sunlight at all. Okay. But then on the other hand, when you're tilted toward the sun, you'll have 24 hours of sunlight, one day a year, and several days a year up here. Now, is it very bright light? No. The sun never gets over, say, 30 or 40 degrees up. Well, in fact, 20 or 30 degrees up. Because you're that far north of the ecliptic and the equator. You just don't get that much sun. It's just the sun, on those days it's 24 hours of sunlight. Here's what's happening. In the east in the morning, the sun is still sitting right above the horizon. Okay? And then at noon it gets up to here, and then in the evening it gets down to here, and at midnight it's just above the horizon. It just does this to the horizon all day long. Never gets very high. Never any direct solar radiation or anywhere close to it. That's on the warmest day of the year. On the coldest day, it's never up at all. It's just below the horizon part of the time, and way below the horizon the rest of the time. It's amazing. Okay. All because of the tilt of the Earth. All right. So this produces, those are the reasons, the factors behind it. Oh, and by the way, I didn't mention this. When we're talking about the different plants, I just saw the picture of the lemon tree. Citrus only grows in tropical to subtropical areas. Florida, South Texas, some parts of South California. Now, New Orleans, they have satsumis, which are some type of a citrus. It's kind of akin to mandarin oranges, okay? They can tolerate a little more cold weather. My wife loves Meyer lemons. So we have 2 Meyer lemon trees, but they're in pots. And we put the pots on rolly things so that in the wintertime, on those days when it is going to get below freezing, we roll them into the garage so they stay out of the really coldest temperature. But then in the day, if it's going to get above freezing, we roll them right back out so they get the sunlight. And we have lemons most year. This year we have one. Last year we had a bumper crop. I don't know what the difference is. It's something about when they were blooming, we had a cold snap, and I think it killed a lot of the things, even in the garage. Okay. Our peaches that we have here won't grow in. Peaches require 200 hours of sub 40 degree temperature. If they don't have it, they're not going to make a good peach crop. Okay, so they can't grow in Florida because they don't have 200 hours of sub 40 degree temperature. Usually, most winters. Pecans have a long growing season. When I was up in Nebraska, I knew of one major pecan tree that actually bore pecans, and not every year. Okay, down here pecans is not yet, just about all the time. So you see, there are those climate zones. They make a difference in our fruits, vegetables, what we grow, what we don't. Okay, so now let's look at the climate zones. I just happened to see those and remember I forgot to say that. Okay? The climate zones are defined in terms of yearly temperature averages. And guess what? They follow very directly to what the globe was showing us. We have the tropical climate zone near the equator, receives the most solar radiation, in general, hot. Hot and hotter, that's basically what you got in the tropical climate zone. Now let's go to the other extreme, the polar climate zones. Least solar radiation any time of the year, some time of the year, no solar radiation. They're cold and colder and coldest, okay? Constant daylight, part of the summer, but not very intense daylight. Like I said, the sun never gets very high. It either is just above the horizon at midnight to moderately up in the morning, barely breaking 20 to 25 degrees in the middle part of the day, and going back to the teens at night and just above the horizon there. It's not much, but constant daylight. And then constant darkness part of the winter. Absolutely not. The temperate climate zone, that's where we live. Intermediate between the others. You have longer days in the summer, longer nights in the winter, but you always have some sunshine. Okay? Temperatures vary a lot. They're intermediate between the others.
Excuse me, I'm sorry, but I got a question. So that means that, so it's true that we get longer days in the summertime and shorter days in the winter.
Yeah, it's shorter. Okay, when I say days, sunlight, longer periods of sunlight in the summer, shorter periods of sunlight in the winter.
So that means
our day is still 24 hours, but the daylight part of it is what we're talking about.
So that means,
daytime.
I'm sorry, like in the summertime we just gonna get short amount of nighttime,
Yeah.
and then in the winter we get longer times.
Yes, exactly. Like I think we figured it about 14 hours of daylight in the summer, and only 10 hours of nighttime. In the summer, we're reversed in the winter. 14 hours of nighttime and only 10 hours of daylight, approximately. Okay, just to have some rough numbers. Now, rainfall patterns shift seasonally. Now, there's some areas of the world that is a major climate issue. You call those the monsoonal areas. I have a friend who is a missionary in Cameroon, which is in East Africa, fairly close to the equator, just north of the equator. Okay, I don't know if anyone ever picked up the city Yaoundé, Cameroon, in your you did the latitude longitude, but that I think was in the cup. Should have been in the African cup. They don't talk about summer and winter or fall or spring. They talk about the wet season and the dry season because the rainfall patterns shift majorly down there. The temperature is always fairly moderately warm. In the dry season, it's really hot, okay, because you don't have the moderating effect of rainfall. And the rainy season is a bit more temperate, tolerable. But it either rains or it doesn't rain, okay. So that's a monsoonal type situation. I'm glad we don't have that here, okay. If I were to ask you what on average the driest month of the year would be, what would be your guess for us here in Alabama? Driest month of the year. What would be your guess? Make a guess. November? Actually, you're pretty close. It's October. But we don't notice droughts in October because nothing really is growing in October, okay? The temperatures are cool, so even though there's not a lot of moisture, plants aren't drying out as badly. I was expecting someone to say July or August. Now, this July and August, we didn't have very dry months, but sometimes you can. But you see, if you go more than, say, 2 weeks without rains, everything suffers, in the summertime because it's so stinking hot, You have to water and water and water your plants, okay? But in the October, you may have almost the whole month go, and you don't really notice it because a lot of plants are dormant and the other things. So yeah, we do have shifting rainfall patterns here, but not nearly as bad as they do in some areas. We are so fortunate in where we live,
3 minutes left.
3 minutes? Oh my goodness. Here's the picture of that. Now you see what we call the tropical climate zone isn't exactly in between the Tropic of Capricorn and the Tropic of Cancer. There's the dotted lines there. Some portions are outside, some are inside. It varies a little bit. There aren't any straight lines on the, governing this. It's lots of factors. The amount of water, the amount of land, the patterns and stuff like this. The temperate, up here, the temperate area is pretty big. Some of it goes below the Tropic of Cancer here, and not much of it extends above the Arctic Circle, but this part right here does, okay? Northern Norway, remember Alta Garden? It's 70 degrees north. It's well inside the Arctic Circle, but that's still somewhat considered temperate just because of patterns that we have, okay? Whereas down here, look at this, the polar extends way beyond the Antarctic Circle, okay? I'm not sure why. My guess is because of the tilt of the Earth. Remember, in the wintertime, they are also so far from they're a little bit further from the sun. So that's my guess. I don't know if that's the main reason. Here, the southern part, this is called Cape of Good Hope, I believe it is, at the tip of South America. That's really bitter weather down there. Just about all year long, but especially in the wintertime. It used to be that ships going to the Far East had to sail around that, and that was miserable. There's so many shipwrecks there. Or they had to sail around this way. That's Cape of Good Hope is here. Cape Horn is down there. Cape Horn was really, really, it's much further south than it's actually in the polar region. Okay. Here in northern Australia is tropical, but most of Australia is tropical.
Got 1 more minute.
Okay. This is not, in my mind, this is talking about the rainfall, and this is sort of ridiculous. This should be just as wiggly and squiggly as the previous one was. You know that it's not dry here and wet there. I mean, nothing is that abrupt anywhere. Okay? So your wettest is around the equator, but then you have a dry region on either side of that, and then not quite as wet, wet, but not as wet as down here and here, and then these are just so cold it doesn't matter whether it's wet or dry. So we happen to live in a wet area, in a warm temperate area. I mean, we are ideally situated. How we got so lucky. Okay. We'll begin next time with regional climate influences. Okay? that's where we'll begin. Okay. Okay. We're not stopping at 3:15 today. It's 3:45.
You said 3:50 because of our lab for the next chapter from last chapter.
I know, but that's 2 hours. We go 3:45 to 5:45. We don't have a test today.
But I still got to make up mine.
Okay, but you can do that. Yeah, whenever you want to.
You said don't stop till any time after 3:15.
What's that? Did I say 3:15?
Yeah.
I thought you did too.
Okay, I'm sorry. It's supposed to be 3:45. Okay, that's what I was thinking. Wow, that time really slipped by. No, we go 2.5 hours of class and 2 hours of lab. Okay, so we still got a little bit of time to go. Okay, so did we get everything said here? I think so. And the lines don't break like this. Okay, they're smooth, they're rugged, and they're not exact. Okay, so I don't really like this one, but it does give the wettest around the equator, the driest, actually either side of the wettest, and then the wet on either side of that, and then cold. Whether it's wet or dry, it doesn't matter. But look at this. For Mexico and much of Central America in the dry area. Just about the whole continental U.S. is in the wet area. This one little portion here, my brother says that's us in Georgia, that's where the driest part of the county, he said, the country, but not quite. They have some very dry here. So you see, these lines aren't exact. This dry area extends up into our southwestern. So these are not, this is, I think, a very important picture. It just gives the general pattern. Okay? Now, so let's look at the regional climatic influence. I'll take this off because that's not where we're actually stopping. Okay? Okay. 4 major factors on the regional climatic influence. Okay? Not the global, but the regional. 1 is altitude. Now, actually, 1 and 2 to me are awfully close to each other, but the number 1 is altitude. How high are you above sea level? The higher you are above sea level, the air radiates more energy back into space. Okay? Think about that. Our atmosphere covers the entire globe. So if you have high altitude up here, you have less atmosphere above you. So more of the radiation goes back right into into space. At lower altitudes, less radiation goes back because you've got a big, thick atmosphere that acts like a blanket, basically. It traps a lot of the energy. Okay. Now, you might say, well, aren't mountains high altitude? Yes, they are, but see, they are abrupt. When the altitude, they're talking about the general increase in elevation. And that usually happens as you go from the coastline to the interior part of the country. Somewhere in the interior, you're generally rising up gradually, okay? Mountains rise up abruptly, okay? Now, of course, the cooler air, the high altitudes here, altitude is still important there. Now, here is the good way to express this. In the book, if I'm not mistaken, they say it a different way. Let me see if I can find it here. In the book, they use the U.S., okay? And what is stated in the book is that the western slopes are usually more precipitation, the eastern slopes less. That's because in the U.S. you have prevailing westerly winds. That wouldn't be true in an area in the tropical area or in the polar areas. That wouldn't be true. This is true. The upwind slopes receive more precipitation, the downwind slopes less. It just happens to be in the U.S., the upwind slopes are the western slopes and the downwind slopes are the eastern slopes. this is the best way to express it. So just keep that in mind. Now, what is one of the wettest cities in the U.S., or at least reputed to be? Seattle or Washington. Everybody thinks it rains there all the time. They have, they have a little saying for it. It's not sun spots, it's sun, short periods of sunlight. And everybody wants to get out and be in the sun when they have these periods of sunlight. Because on the Cascade Mountains are here, so anything on the upwind side of that, the moist air coming out of the Pacific Ocean goes up, hits those snow-cup, the mountains there, and all the precipitation runs here. One of my favorite places ever is a place called Muir Woods, right on the coast, north of San Francisco. I think it may be Marin County or Sausalito, somewhere there, but on the coast. And that's where you just have these giant sequoia trees. Not the sequoias you see somewhere. And they're massive trees because they just get rainfall just about all the time. In fact, quite often the top of the trees are in the clouds, and they're getting moisture directly from the clouds. I mean, they're that tall. So the upwind slopes or the moist slopes, downwind side, though, it gets drier. In Washington State, the western side of Washington State is green. The eastern side of Washington State is not quite desert, but it's much closer to it. So Washington State is somewhere out in the west. University of Washington is on the east. It's like they're in different states. I mean, they're very different climate, especially rainfall climate. Okay. With that in mind, you would think as far east as we were, we would be dry. And we would, except for the good old Gulf of Mexico. Pumps moisture in here, whereas out west, same area, but go around there, dry as a bone, Mojave Desert. Miserably hot, dry desert. Around here, the Gulf of Mexico, that's what keeps us wet. We are really lucky where we live. Okay? All right. So, upwind slopes, more precipitation, downwind slopes, less. These are regional climatic influences. Okay, next, large bodies of water. Okay? What difference does that make? Well, at least two. The two big differences. Temperature and moisture. Okay? Large bodies of water tend to moderate your temperature changes. Again, that's why Hawaii has almost constant temperature. It's surrounded by water. Warm water. Okay? Almost year-round warm water. So they have very little temperature change. Their Christmases are just about as warm as the 4th of July. I mean, it's just the same all year long. Okay? But the other thing, and the reason for that part, is the water has the highest specific heat of just about any other substance on the planet, which means it takes more heat to warm water, say, a degree Celsius or Fahrenheit, than it does any other material. There was a physics meeting that I used to go to pretty regularly, and one time they had this series of experiments that we were able to do, and they had this circle made out of metal with holes drilled in the side. I think there were 6 or 8 holes drilled in the side. And they had these pegs that you could put in the hole. And under the plate, they put a flame, a Bunsen burner, okay? And you put your piece of metal, this peg, into the hole. But all the pegs are made out of different materials like aluminum, iron, lead, zinc, nickel, various metals, okay? You put them in and hold them in there until you couldn't hold them anymore. And sure enough, somebody would let theirs go way before anybody else. Now, were they just a wimp with a low tolerance for pain? No, they happened to have the aluminum peg, or maybe the other peg, because the different pegs had different specific heats. It took more heat to change the temperature of some pegs than it did of others. What you were feeling was temperature, not how much heat, temperature. And because some metals have very low specific heat, it doesn't take much heat to change the temperature and get it so it doesn't burn your hand. Whereas other metals would be a much higher specific heat. Well, if you had a metal like water, you would be the last one to pull out. Of course, water is a metal because it has the highest specific heat about any substance. Okay, so what does that mean? Have any of you ever gone to the beach in the summertime? Okay, on the Gulf of Mexico? Yeah. What did you notice as you were driving down? I don't know. Here's my experience. You leave here in Birmingham area and you go south. And gradually it sort of gets warmer and warmer. Montgomery is usually a few degrees hotter than Birmingham, sometimes several degrees. You keep on going down, it gets warmer and warmer. But somewhere down there, when you get just short of the beach, suddenly it feels cooler. Now, part of that is the air blowing off the thing, but that's because the water has a higher specific heat than the land, so the water temperature is almost always cooler than the land temperature. So therefore, it does feel, and it is cooler there. Have you ever gone to the beach in the wintertime? It's warmer than it is. You know, you go down and you just keep getting warmer and warmer. You get to the beach, it's really nice most of the time, you know, because water has a higher specific heat. It retains that heat longer in the wintertime and loses it slower in the summertime. Okay? Okay. So large bodies of water. Gulf of Mexico is certainly one. The oceans are one. But even, has anyone ever been to either Rochester or Buffalo, New York? I haven't either. They have what they call lake effect snow, because they're right east of the Great Lakes. And the water blowing across the wind blowing across the Great Lakes picks up moisture, hits the colder land mass, and drops snow. That snow didn't come from the Pacific, it came from the Gulf of Mexico. I mean, not the Gulf of Mexico, the Great Lakes, goodness, I'm not talking about. The Great Lakes, that's where it picked up that moisture. And those prevailing westerlies do it. So Buffalo and Rochester are going to get a lot more snow in the wintertime than just about any other part of New York, even though this is right off the Atlantic. It doesn't get it much because of the lake effect snow. So large bodies of water do contribute big time to the regional climate. Okay? And then the next one is ocean currents. We're going to hit this really bigger in the next chapter. So that's what we're talking about in the next chapter with the oceans. Okay? But the ocean currents can bring water nearby at a very different temperature from the land. And again, here's the Gulf of Mexico for us. The prevailing winds and sort of currents too in the tropical area are east to west, going this way. Our winds in the temperate area are west to east. That's why we were just everything we're talking about. So the winds coming this way, that also brings the moisture this way. So basically the warm tropical waters from down here move up the coast of South America into the Caribbean Sea and into the Gulf of Mexico. And it sort of stops it there. So the Gulf of Mexico, these warm currents carry it in there. Now, some of those warm currents actually twist around and go past Florida and up the eastern seaboard. Well, that's called the Gulf Stream. They don't come from the Gulf necessarily, but some of the water from the Gulf does make its way out and go up around there. The Gulf Stream keeps our entire eastern seaboard absolutely ice-free all year long. We are so lucky where we're located. If we were at the same thing over here in same latitude, here let's go around the same latitude over here in Siberia, okay? Same latitude, frigid, ice in harbors, you can't have free travel in the wintertime there. Everything sucks in with ice. Same latitude that we are, we're perfectly free of ice. All up and down. Maybe a little bit in Maine they get maybe a little crunch or something, but not enough to deter trade. Over here, hanging up in the wintertime. Okay? That's the Gulf Stream. Now, we're not the only ones that benefit from that. The Gulf Stream comes up here, and basically, in some of these areas way north here, used to be some of the greatest fishing areas in the world because of that warm tropical water coming up there and mixing with the nutrients they had here. I think one of these areas was called the Sargasso Sea, and there was Grand Banks, just fantastic. But, well, guess what? We have fished it. Not just us, the whole globe has fished it to death. I'm not sure we'll ever get back the great fishing that we used. Oh, there's the Sargasso Sea right there. Okay? That normally you have the Japanese, the Chinese, U.S., Europe, everybody would come in there when they found out how great it was, fished it to death. So I don't know if we'll ever come back. And the Pacific, they got other problems. We've dumped so much trash. There are certain areas of the Pacific that are completely dead because there's too much particulate plastic floating in the water, and the plankton try to eat the plastic thinking they're the food source, and it's not. And they don't live, and then they die, and then the sardines die, and the other things die. So there's some real dead areas, mostly because of pollution there. Overfishing here. Probably some overfishing there too. Well, not just us, but now poor old Canada, there's another current that comes south from here, and it keeps most of Canada frozen in the wintertime. Poor Canada. They give all the soil to us, and we rip off the ice. Okay? But the Gulf Stream moves over here until it hits England. And England, as far north as England is, they still are ice-free because of the Gulf Stream. Okay? Go on over the same latitude here, and you're into incredibly cold temperatures here. In fact, Mongolia, and again, this area here, not hospitable. England, that's how she became Queen of the Ocean. She never froze up in the wintertime. Okay? Good for her. And she became the mightiest seagoing country in the world for the longest time. So the ocean currents can bring water nearby that has a very different temperature from land. Now let's go to the west coast. And by the way, the Gulf Stream, the beaches in New England, Long Island, even up Boston, what they call Cape Cod, really nice in the summertime. Fantastic in the summertime. Go over here to San Diego. If you've ever been to the beach in San Diego, in the dead of summer, most people are in wetsuits. Even though the land temperature is quite nice, you have Pacific currents that go down this way. So cold air coming this way, cold water coming this way, keeps San Diego, the beaches there, very, very cold. Yeah, you would think. The weather there is perfect. I mean, fantastic weather, temperature on land, but the beaches are not. You'd much rather be on the beach in New Jersey than you would in Massachusetts than you would in the water in San Diego. Really strange. Those ocean currents can make a big, big difference. Much different temperature than the land. Okay, here are some of those currents. As we see here, you have the Gulf Stream comes up, keeps the Gulf of Mexico, or the warm North Equatorial Current keeps the Gulf of Mexico and the Caribbean balmy warm all year long. Gulf Stream moves on up the coast, keeping all the ports in the U.S. nice and ice-free. But the Labrador current comes around Canada and keeps much of it frozen in the winter. And they're right next door to each other. Okay, you see a similar thing over here. The North Pacific current, which is relatively warm, it goes up and keeps Alaska and the west coast of Canada ice-free, and much of Alaska, now not up here, but much of southern Alaska ice-free, even though it's way up north. But then the split that comes down here keeps San Diego and Los Angeles and all those beaches way too cool to really go out and sunbathe. You know, you can sunbathe, but you can't get in the water that much. You can, but it's going to be cold. Most people wear wetsuits. It's really bizarre. Here you see there's a cooler current moving up here. That isn't described too well because this is tropical Cancer. There's the equator. Where's that cool air water coming from? It's from way south down here, and that keeps this coast. In fact, Quito, Ecuador, right on the equator, is number one, get these cool water coming in here, but number two is at a high elevation. So Quito, Ecuador, even though it's smack dab on the equator, is a very pleasant place to live. Okay, down on the beaches, hot and salty, but up where it is much nicer. But those currents help keep it moderate. Okay. All right. Now, how do we describe these climates? Now, the very thing I was saying I didn't like about that global map that you saw earlier, the problems are there aren't any sharp boundaries, okay? The boundaries are diffuse. They vary year to year sometimes. They may move a little bit up and down, east to west, something like that. So that one that just shows the sharp thing, no, nothing is like that. No two places have exactly the same climate. We talk about them as if they're similar. For instance, the Napa Valley in California has a fairly similar climate to the Mediterranean, okay? But it's not the same. It's similar but not the same. That's why they grow great grapes in wine country in California like they have in Southern Europe. But it's not the same. The wine connoisseurs will tell you how different it is, but I'm not a wine connoisseur, okay? So no two places will have exactly the same climate. Climate is so variable. A description of the North American climate zones is what's going to come next. And this is a very interesting and pretty detailed description. And since we're within probably 5 minutes now?
We're at 6.
6 minutes. Okay. We can't get this whole slide done in 6 minutes. I don't think any fair way. So what we'll do, okay, we'll start with major climate zones next time. Okay, and this map you saw here, we'll be using that extensively. Okay, and this will be just for mostly the U.S., but mostly North America. A little bit of Central America, but mostly U.S. and North America. Okay? So why don't we then, do you want to have a little break time, or do you want to go right in the lab?
A little break.
I would too. I sure need a bladder break myself. So we'll pick up here next time. So let's take a quick break. So I'm going to pause this. I'll need the projector for this part, but if so, I'll turn it off. Okay. I think we're recording now. Yeah. Today's lab is on topographic maps. Okay. Now, maps are anything that show basically the landform and what's there. There are road maps, and most of the lines on the road maps will be roads, streets, highways, interstates, whatever, with some other lines that would show, say, county boundaries or state boundaries or, or things like that. That's a road map. Some of you may have remembered from the past reading about road maps. Most people don't use them anymore. They use GPS. But we're talking about a different kind of map today, and that's a topographic map. Okay? Does anyone know what a topographic map shows? Basically, it shows differences in elevation. Okay? Now, that's what topography is. Graph means picture, basically. So it's the topographic picture. Three-dimensional shape of a surface, including mountains, hills, valleys, and that type of thing. Now, they may also show roads and population centers and things like that, but political boundaries, counties, states, and things like that. But basically, the purpose of the map is to show topography. Now, here's sort of a dumb story that goes with it. We had an Italian kid live with us 1 year. Actually, we knew his parents from, his father was a classmate of my wife's School of Public Health. They were in the doctoral program together. And they were just really good friends. And we found out much later that he and his wife had just been married just a month or so, a few months after Karen and I got married. But then, so we had been married couples, similar time frames. And we got along with them really well and had a lot of fun with them. But after Fabio graduated and went to Boston, worked for a pharmaceutical company, that's when Rita had their first child, Giacomo. And he was born in the U.S., in Boston, so therefore he was a U.S. citizen. He's a very bright kid, and many years later, Fabio came back to do a year postdoc at UAB, and we got to meet all three kids. He had two sisters born back in Italy after they moved back to Italy after a year in the U.S. And so we got to know the kids, and they had a year of school here in the U.S. They liked it a lot. We liked them. They were a lot of fun. That was junior high to the youngest was maybe elementary. Well, then they went back to Italy again. And then we went over to visit once when Karen had meetings over there, and it was at a time I could go. I think it was around Thanksgiving maybe. And so we went over and visited there. And by this time, Giacomo was in high school. And he sort of entertained us while his parents were busy. His dad had to go to work, and his wife had to run things around. So he entertained us, and we just got along so well with him. And shortly after that, his dad and mom were wanting to give him the opportunity of going to college here in the U.S. or in Italy, whichever he preferred. But they felt like he'd have a better chance of going to school in the U.S. if he graduated from U.S. high school. So they were trying to find a program that he could do to graduate from U.S. high school. Well, after we got along with them so well, they got to thinking, well, could maybe live with Charles and Karen for a year. And they looked in the high schools in Birmingham, and they found one that Fabio knew somebody who knew someone who was at the school. It worked out that he came and lived with us. Well, he was a pretty good athlete, but not in the traditional sports. His sport was orienteering. Have any of you ever heard of orienteering? Okay. What that is, the military does it to a certain extent. What they do for orienteering, they go out to a place, someone has already laid out the course, but no one knows that, what it is. They give them a topographic map with something like 10 stations located on it, in a certain order. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Just all over. You crisscross many times, and you have to hit them in the right order. But all you have is a map and a compass. That's all you have. You can have a watch to adjust your time. And basically, you go follow the compass on the map where you need to go and follow the topographic map and find those stations, usually out in a wooded area and stuff like this. and you're just on your own, okay? And so that was his sport. So he knew how to read a topographic map. In fact, he had a great sense of direction. And he did his science project based on orienteering, and he came in third in just about every competition he went to. It was such a unique thing. He would pass people who had beat him before, but he's still right near the top. Fortunately, only the top 2 from Alabama went to nationals. We were sort of glad of that because we had to go with him everywhere he went to and he was tired of it too. But anyway, but he did well. Okay. So that's what we have this. There's other maps called geologic maps which show different distribution of rock bodies and stuff like that. We're not dealing with that. In fact, our globe sort of is that. It has raised mountains areas and stuff like that. Now, our topographic map, it shows the elevation differences by means of what they call contour lines. These are isoclines. Iso meaning same, clines meaning elevation. Okay? So lines of equal elevation. The map at the bottom of the page is a little illustration of a topographic map. And you can see here there's a bluff on this side, a hill on that side, some hills in the background. Now, you can't see the hills in the background, but there's a river, a stream that comes down in the middle here, or a valley anyway, okay? So what we have here, over here where it goes up abruptly, look how close the contour lines are with each other, because you're going almost straight up. So the contour lines are very, very, very close together. On the hill over here, they go up much more gradually, so the contour lines are a little further apart. But notice there are some valleys going down the hill, and those you can see on the contour map too, because their elevation drops faster than the other part of the hillside. And you have the peak up here at the top, about 260, what is this in feet? Yeah, 260 feet. And the one over here seems to be about 275, a little bit taller. So you see how to read the topographic map. The interval here, you see they list at 100, 200, and stuff like that down to 20. But if you count the lines in between, 5 lines in between, so there are between 100 and 200. So that means the lines are every 20 feet, okay? Those are your contour lines, okay? And that's your contour interval, is 20 feet. All right. Most of what you read on that page and that you'll read on the next page will be answerable to the results that you read later. So read that first page and most of the second page. We're not doing the materials, okay, and the procedures. Not doing that, but we are, based on the reading here, on page 345 and the top part of 346, you can answer the 5 questions on page 347, or at least I'll say the 4 questions on 347 and 348. So that's the first part of the lab. Read the first 2 pages, answer those first 4 questions. The second part of the lab is then on page 349. And this is where you'll need your computers. So work with one another, share the information, or I'll take you to a lab if you need to go to one. Now, they give a website here, but earlier this website had been taken down. If you can't get something on this website, then here's what you do. Use a search engine, whatever search engine you prefer, to, I want to say Google it, but to search for Devil's Tower National Monument in Wyoming. Devil's Tower National Monument in Wyoming. Okay? And what you look for is either relief map or topographic map. Sometimes they're called one, sometimes they're called the other. Relief map or topographic map of Devil's Tower National Monument in Wyoming. And when you find that, then you answer these questions. Number 1, what is the elevation of Devil's Tower? What is the contour interval like the one we just saw at the front page on 345, that contour interval was every 20 feet. You'll need to determine what it is on your map. Okay? Now number 3 says, what is the approximate height of Devil's Tower? Is that the same as number 1? What is the elevation of Devil's Tower?
No.
Why not?
Because height is different from elevation.
Yeah. Height is like how tall it is.
Yeah.
Elevation is like
how far above sea level.
Exactly, you got it. Elevation is how many feet or whatever they measure it in above sea level, whereas the height is how far it is above the surrounding landforms. In other words, like you said, how tall it is from the surrounding thing. So the elevation is always going to be greater than the height, unless you're in the Dead Sea Valley or Death Valley in California or something. Okay? Another question here is, what is the top of Devil's Tower like? And then the 5th one is Devil's Tower too steep to height to the top. So you should be able to find that from your website, either this website or whichever one you find. Share with each other.
Okay, what kind of map?
A contour map or a topographic map or a relief map. They'll use those 3. Mostly relief map or topographic map. Okay. Well, that gives you only 10 points worth. Where are our next 15 points coming from? Well, they're coming from this, the topographic map of Alabama. Okay? Let me get back close to the microphone so people can hear it. So if you're not here, you'll probably need to come in, or if you can find one on your website or somewhere, the topographic map. So here's the things that you'll put, and I will turn on the projector for this. Here's basically what we want for this. You got 15 points worth of information, and here's what you're going to put.
So the 10 points that we've got here is on the invitation to inquiry, right? Okay,
yeah, that's 5 points. Your other 5 points are the 5 questions on page 347 and 348. The first 4 of those come from your reading on the first 2 pages. The last one you'll do at the end of the lab. And then the next 5 points are based on your search of Devil's Tower National Monument. And then your next 15 points come from here. And here's what you're to list. Let me get my pen set up. Okay? First, page numbers. Okay? Now, what you'll do is open this book, and most of you, when you open it, you'll get to pages 30 and 31. You don't have to go there. That's just where it always opens to, it seems like. You can use that one if you want to. That's where we live. That's where we exist, on those pages. Okay? And what you're to look for here, now you see streets listed here, you see the highways, you see the interstates, you see all those things, but if you look carefully, you'll see these little thin lines here. They're sort of grayish in color, and those are the topographic lines. So what you're to look for, I'm just going to say on whichever page, they always come in pairs, okay? 24 and 25, 16 and 17, 36 and 37. They always come in pairs. So put the page numbers that you're doing with, and then look for an area with close topographic lines or contour lines. And if you need help, ask me and I'll help you see these. Close. So find an area. This is not an answer, but for instance, what if the close lines were at Vanderbilt? Then you'd put Vanderbilt. Or Pleasant Grove. Nate, there's actually 2 Pleasant Groves on here. There's one over here and one over here. So you have to be careful with that. I've never noticed that. I can't find. Oh, there's this one. So there's 2 places on this one map called Pleasant Grove. Okay? Or Henry Ellen. Or, something right here where the lines are close together. Okay? Now, the next thing you answer is, what does this mean? where the lines are close together. Okay? When you do your reading and look at these, I think you'll see what that means. Then look for an area on those same 2 pages where the lines, the topographic lines, the contour lines, are far apart. Okay? Someplace. And again, that could be West Jefferson Wildlife Management Area, or Blue Creek Mine, or something like that. I'm not saying that's it, but something on the map that you can identify where the lines are far apart. And then you answer, what does that mean? What does it mean for the lines to be far apart? Okay? So, area where the close contour lines, what does that mean? Lines where they're far apart, what does that mean? Okay, do this for 1, 2, 3, 4 sets of page numbers. That will give you 4, 8, 12, 16 points. So that gives you your other 15 points there. You plus 1, okay?
This is telling me that the elevation and the height are the same thing.
Who said? Google? No. Okay.
Well, I mean, I'm in looking through.
Right.
Well, you know,
Okay.
depending on your location, it could mean the same. It just depends.
Well, yeah, if you're something right on the beach, then your elevation and height would be the same culture that above sea level. But you see what they're saying, that's one definition of height. The definition they're asking for here is height above the surrounding area, not height above sea level. Both of those are heights, you know, elevation, but they're asking for how high above surrounding areas, not how high above sea level. The first question.
It says 1,267 feet above Bella Fortune River.
Okay.
But the base to the top is 867.
Right, that's the height. Exactly. Okay. Now, okay. Everybody understand? 4 sets of pages from here, find lines close together, lines far apart. Now, if you get down into lower Alabama, LA they call it, you get down there, everything is flat there. You may not even be able to find any contour lines. If you can't, go to the different pages. There's plenty of pages in here that have good contour lines. So don't get stuck. Ask me if you have questions. So if I were y'all, some people be reading the text and answering those questions. Some people be looking for Devil's Tower, and others be using this, and then swap them out so that everybody can finish at a reasonable time. If you all do them all at the same time, then everybody's going to want that book at the same time. So take advantage while that book's free to use the book. Okay? You want me to leave this up, or do y'all understand what you need to do? Okay, I'll leave it up. Okay. And you have plenty of room either, I'd say, on the back page to do this, the page 349 to answer those 5 questions, and then... Okay. So, any questions? Oh, and by the way, this board was found in the room after class last time. Does that belong to you? It was over near your desk. Did you notice it here?
It's been over here.
Been over there for a long time. Okay, well then I'll leave it out here.
Well, I need a third essential cord.
What's that?
I mean, you don't need that.
Okay.
Excuse me?
I put it up because they thought it was yours, and I didn't want it to disappear.
I've been here since the class started.
Okay. All right. If you have questions, please ask. I'm going to pause recording now